Welcome to homework.
Let's write down Newton's second law for the cylinder, the rotational form of Newton's second law for the cylinder, and the regular form of Newton's second law for the bar. Here FCB is the force exerted on the cylinder by the bar. FF is force of friction. MC is the mass of the cylinder. A is the linear acceleration of both the cylinder and the bar. FFX is the x component of force friction. R is the radius of the cylinder. IC is the moment of inertia of the cylinder in relation to its central axis. So this entire equation is written with respect to the central axis of the cylinder. Alpha is the angular acceleration of the cylinder. FBC is the force exerted on the bar by the cylinder. FSL is the force exerted on the bar by the left spring. FSR is the force exerted on the bar by the right spring. MB is the mass of the bar. Let's take a closer look at the conventions. Delta X is the x component of the displacement of the bar in relation to the position of equilibrium. So the second temporal derivative of delta x two dots, is equal to the x component of the acceleration of the bar, just by definition of acceleration. Force exerted on the bar by the cylinder is equal and opposite to the force exerted on the cylinder by the bar, according to Newton's third law. So the x component of FBC is equal to negative the x component of FCB. I denote the x component of FBC as f, just for simplicity. It is going to be also equal to the negative x component of FCB. Alpha is the angular acceleration of the cylinder. Because the cylinder doesn't slip, the angular acceleration of the cylinder is equal to the x component of its acceleration divided by its radius. I'd like to explain why I have minus here. In order to accelerate the rotation of the cylinder clockwise in the positive direction of rotation, force of friction has to be directed toward the left in negative direction. In order to accelerate the rotation of the cylinder counterclockwise in negative direction, force of friction has to be directed toward the right, so in positive direction. The sign of the x component of force friction is always opposite to the sign of the angular acceleration of the cylinder. For this reason I have minus here. Let's replace the first and third equations with their x components and replace the moment of inertia of the cylinder with respect to its central axis with 1/2 mc times r squared, because the cylinder is uniform. In general, the moment of inertia of a uniform cylinder in relation to its central axis is equal to 1/2 its mass times radius squared. I replaced all the vectors with their x components. So FCB gets replaced with FCBX, but FCBX is equal to negative f, so I have negative f here. Force friction is replaced with FFX, acceleration is replaced with AX. Here FBC is replaced with FBCX, but FBCX is equal to f, so I have f here. The sum of FSLX and FSRX is replaced with negative 2k delta x. Here k is the spring constant. Please note that FSL is always equal to FSR in both magnitude and direction. And the sign of the x components of FSL and FSR is always opposite to the sign of the x component of the displacement of the bar. Please note that I have isolated f of x from the second equation, and now I can substitute it into the first equation. I have also replaced the x component of acceleration with delta x2 dots. Let's now add these two equations to each other. F and minus f will cancel out. Let's move all the terms to the right side of the equation, and then factor out delta x2 dots, and we finally arrive to the following form of Newton's second law. This equation describes harmonic oscillations, and this coefficient is equal to the angular frequency squared. Delta x varies harmonically over time. This is how delta x depends on time. Delta x naught is the amplitude of delta x, which is also equal to the original deflection of the bar. Omega is angular frequency, which is equal to the square root of this expression. T is time. Phi is the phase shift. Phi equals pi over 2 in our case. Let's take two temporal derivatives of delta x. When you take the first temporal derivative, sine changes to cosine and omega comes out. If you take another temporal derivative, then cosine will change to negative sine and another omega will come out. This is how the x component of force friction depends on the x component of acceleration. This is how the x component of acceleration depends on time. Please note that because sine varies from -1 to 1, the x component of acceleration varies from negative delta x naught omega squared to positive delta x naught omega squared. This is the maximum theoretically possible magnitude of the force of static friction. It is equal to the coefficient of friction multiplied by the magnitude of force normal. The magnitude of force friction should never exceed this value. Let's isolate delta x naught from this inequality. Let's substitute the expression for omega squared into the right side of the inequality. The upper limit on delta x naught is now expressed in terms of the known quantities. Substituting the numbers gives us the maximum limit of delta x naught of 0.0304 meters.